All right, so I'm looking at these ones. So in that first one, remember, you just take the name, convert it to the symbol for each of them, assign the charges, swap the charges, simplify if possible. So we did the first one. So sodium nitrite ends up being Na3N. So calcium is what? Ca. And what becomes the charge? It's a +2. Okay, so make sure you put the plus there. Don't just put a 2. Just make sure you put the plus there. And then phosphide is P. And the charge on that is a -3. Right? So if you look, so phosphorus, same column that nitrogen's in. So now when I swap it, what does the formula become? Ca3 P2. The charge on the calcium tells you how many phosphorus. The charge on the phosphorus tells you how many calcium. So all you're doing is just taking those numbers and swapping them. Don't swap the charge. Don't put a plus or a minus at the bottom. You're just taking those numbers and swapping them. Lithium oxide, so what's lithium? And what is its charge? Yep, it's a plus. And then oxygen is, with the -2. Right, so remember 8 minus its group number tells you the negative charge. So when you swap this, it becomes, and just to know. So if it's just a 1, you can just leave it. You don't have to put the 1. Typically, formulas don't have a 1 if it's just 1. Magnesium iodide, so magnesium would be? And the charge? +2. And then iodide would be an I with a negative. So when you do this swap, you end up with, Mgi2. Okay, so just make sure that you follow those steps. Now, if you're going the other direction, if you're given a formula, how do you name it? So Li3P is lithium phosphide. You always use the whole name of the metal, the first element, first part of the second element plus IDE. So this would be lithium phosphide. What it would be, BeF2. Beryllium fluoride. And then the last one. So Ca3N2 is calcium, whole name of the metal. First part of nitrogen is niter, N-I-T-R, and then you add IDE. So all those always end in that IDE. The non-metals always like the first part of it. So oxygen becomes ox, fluoride becomes fluorine, chlorine becomes chlor, bromine is brome, but you just add that IDE at the end. So then we started talking about the transition metals. And so this kind of goes back to this one. And so with transition metals, and the only transition metals that you have to worry about are these 3. So it is chromium, iron, and copper. Cr, Fe, and Cu. So those are 3 that you needed to know their names and symbols from the chapter 1. But with these, because they're in that group, notice that they don't have a capital A at the top. They're a capital B group. So like the first 2 columns and the last 6 columns all have a capital A. Group 1A, 2A, 3A, 4A. But if you go and look at the group down here, it's kind of like the section that's like doesn't have those top 3 rows. Those are called transition metals. These metals are a little bit different in that they're bigger than the 1 through 20. That they actually have some 4th energy level electrons. Because remember, like hydrogen and helium are in the 1st energy level. And then we did lithium, beryllium all the way across to neon in the 2nd energy level. Then sodium, magnesium, those would go into the 3rd energy level. With this first row, where chromium, iron, and copper are, these transition metals, they can actually lose different numbers of electrons and still become stable. So in all the other ones, you only have a specific charge. Well, chromium can either end up losing 2 or losing 3. Iron's the same way. It can lose 2 electrons or 3. Copper can lose 1 or 2. So since they found that there were compounds with different charges to the metals, they said, okay, well, we have to be able to distinguish between a compound with copper 1 and copper 2. We have to be able to distinguish between a chromium with the +2 and a chromium with the +3 in a formula. So that's where they came up with the Roman numeral. So the example, iron 3 oxide. See the Roman numeral, it goes between the metal and the nonmetal. This Roman numeral tells you the charge on the iron, because it could be +2 or it could be +3. So the Roman numeral tells you that this is Fe with the +3. So iron Roman numeral 3, the Roman numeral 3 tells you the charge on the iron. Now, the other thing's oxide, so what is that? So it's an oxygen, and you know the charge on oxygen, you know it is -2. So if you have the name, you just list the symbol of the iron, copper, or chromium. You list the charge based on the Roman numeral, and now all you do is the same thing. You're just going to swap them, right? So the charge on the iron tells you how many oxygen. The charge on the oxygen tells you how many iron. So the formula for this would be Fe2O3. So I just swapped them, just like what we've been doing all along. That's actually how you tell. Whereas if it was iron 2 oxide, then I'd put a +2 for the iron and do the same thing. So then if I'm given the formula and I want to know what the name is, so I know that CuCl2, what's its name going to be? Cu is what? Copper. So I know that this is the first whole name of the metal, copper. Then that Cl2 becomes what? Chloride. Okay, so notice the name part, that part's the same. The only thing that's different, I need to determine the charge on the copper so that I can say what Roman numeral goes between. Does a 1 go there or a 2? It's a 2. How do you know? So if you look at if you look at chlorine, you know that chlorine is a -1, right? Because it's in group 7. So notice that and copper is a 1. So you see how those are the same? So you can take the number for the copper, tells you the charge on the chlorine, so the number for the chlorine tells you the charge on the copper. So in this, it's almost like a reverse swap. So the formula, just reverse swap it and it'll tell you the charge. So I need to put a Roman numeral 2 between the copper and the chloride. So that indicates the charge on the copper. I will tell you the biggest mistake I see is people want to look at CuCl2 and say that's copper 1 chloride because there's 1 copper. In the formula, that's the most common mistake, is that people want to say the Roman numeral tells me how many. No, the Roman numeral tells you the charge. It'd be nice if it was just told you how many, because then you could just go directly there, but it actually tells you the charge. So if you see, and it's only going to be iron, chromium, and copper, there are some other ones that do this, but we don't really come in contact with those as much, but you are going to see these as we go along through in future chapters, so that you understand. So chromium is either going to be, this one is either going to be a Roman numeral 2 or 3. This one's going to be Roman numeral 2 or 3. This one's going to be Roman numeral 1 or 2. And that's it. Right? So that's all you have to worry. You just have to remember iron and chromium can be a Roman numeral 2 or 3 because they can be a +2 or a +3. Copper will only be a +1 or a +2. So practice some of these ones then. Go back here. right? So the rule, if you have transition metals, they can exist with multiple charges, and it's iron, chromium, and copper only. So what do you always have to make sure you use? You gotta make sure you use the Roman numeral. So you do these four. From the name, write the formula. From the formula, figure out the name. All right, so if I have copper 2 chloride, what does that mean? I put Cu, then what? Plus 2, right? Because the Roman numeral 2 tells me the charge on the copper. So that 2 tells me the charge. And then chlorine has a -1, right? Because it's in group 7, so it's always a -1. So now when I do the swap, what do I end up with? Yep. All right. Iron 2 nitride. So what does that tell you? Fe plus 2. And then nitride would be the -3. So you write the symbol, assign the charge. If it's a transition, the Roman numeral tells you the charge on that metal. Now I have to swap them. So the formula is Fe3 and 2. So in this, what's the name of this one? Chromium. It's chromium 3, and what the end is sulfide. So just doing it a little bigger so you can see. So you know that if you look at sulfur, what's the charge on sulfur? Yep, so you know sulfur is a -2. So notice that the -2 on the sulfur is the same as the number of chromium. So you see that, so that tells you what's the charge on the chromium. Right, so this and this matches, so I know then that's the +3. Okay, so it's like a reverse swap, if you will. Like you can think of it, okay, it's just the reverse swap. The formula is going to tell me the charge. What about the last one? Iron 3 fluoride. And again, if you kind of pull iron and Fe3, you know the charge on the fluorine is a -1 because it's in group 7. So notice that the number of iron is 1 and the charge on the fluorine is 1. So those are both like 1 and 1. So then you know, oh, I can take the fluorine number, and that's going to tell me the positive charge for the iron. So that +3 on the iron is the reason why you have a Roman numeral 3, right? Just remember the Roman numeral tells you the charge. So that one's kind of like, these are really kind of weird sort of charges. And in fact, for all the transition metals, they all have different kinds of charges. But for us, copper, iron, and chromium, those are the only 3 that you have to worry about and remember. The second kind of oddball thing are what they call polyatomic ions. So when you think poly means what? Yeah, multiple or many, right? So a polyatomic ion is one that has a lot of atoms. And so in this, just by definition, polyatomic, it consists of a group of, it's always nonmetals, but together the nonmetals have a charge. The charge is for the entire group of atoms. Whether you're naming or writing the formula for these, you do the exact same things that we've been doing for ionic. You write down whatever the positive ion is, it gets listed first. Negative ion gets listed second. Assign their charges, which are like known and given charges. You swap them to figure out the formula. So for example, if you have a polyatomic, and there are 7 of them, just these 7, there's a whole bunch of them, but we're only going to worry about these 7. So there is 1, 2, 3, 4, 5, 6. The ones that I have in boxes are the ones to know. So I have the hydroxide ion. It's an OH with a negative charge. So that's not the hydrogen with the negative charge. The entire group has a negative charge. The ammonium ion is NH4 and has a positive charge. It's the only positively charged polyatomic. So it's the only one you might see out front. All the other ones are always at the end because they're always the negatively charged ion in the ionic compound. Then we have the nitrate, NO3 with the -1 charge. There's the chlorate, which is ClO3, also with the -1 charge. So notice these ones all have just a single charge. The hydroxide's a -1, the nitrate's a -1, the chlorate's a -1. The ammonium is a +1. But then you got the carbonate. So CO3, that is a -2 or 2 negative. Either one's fine. Remember, I don't care how you write the charge for it. -2, 2 negative. Either way, completely fine. So if you put it like this, -2, that's right as well. So it's CO3, a carbon with all those oxygens is the carbonate. Just like the nitrogen with extra oxygens is a nitrate. The chlorine with extra oxygens is a chlorate. Carbon with extra oxygens is a carbonate. So sort of like the first part of their name as a polyatomic deals with like what other non-metal besides oxygen it has. And then here's the other 2. So the other 2 are the sulfate, which like the carbonate is SO4 with the -2. So sulfate is a sulfur with a bunch of oxygens. It's got 4. And then the last one is phosphates. So the phosphate is the only one with a -3 charge. So notice there's a lot of them. There's sulfates, there's sulfites, there are hydrogen sulfates, hydrogen sulfites. There's like a lot of polyatomics, but these are the ones that are really the most common ones. And when you have to give these as a solution, these are the ones that you're typically going to see. So I've got them listed. No, see now it's starting to do its thing. So I've got them listed just in one. I'm listed in one right here that I'll show you. Right there. So there's the 7. The hydroxide ion is OH with a -1. The ammonium is NH4 with a +. The nitrate is an NO3 negative. Chlorate's a ClO3 negative. The carbonate and the sulfates are both -2s. Carbonate is CO3 with the 2-. Sulfate is a SO4 with the 2-. And then phosphate's the one with the biggest charge. And it's a PO4 with a -3 charge. So in terms of medicine, healthcare, hydroxide, this is a characteristic ion that you find in a base. So when you talk about acids and bases, the hydroxides are characteristics of bases. When you check someone's ammonia level, if a patient has kidney failure or has liver failure, then you may find that their ammonia level circulating in their blood is higher than it should be. So they may check the ammonium ions because that's how ammonia would float through the blood. continuing down, if you go to the phosphate, so in DNA, DNA is made of a double-stranded helix. The strands are made of sugars and phosphates. So the phosphate is that PO4 with the -3. So that's why DNA is negatively charged, because of the number of phosphate ions that it has composing the strands. So whether you've got a formula or if you've got a name, formula or name, you're still going to do it exactly the same. The only kicker is you have to remember when you see sulfate, you have to remember that means it's SO4. It's not sulfide, it's sulfate. So when you do the naming, you use the entire name of the polyatomic ion. So for the first one, NaOH, Na would be sodium, and then OH is hydroxide. So the name, sodium, and then hydroxide. So you don't have to worry about figuring out like the IDE first part. It's just the hydroxide ion is this as a whole. So NH4Cl would be, the NH4 is the ammonium ion, so you would just call it the ammonium, and then having the chlorine, you use the first part of the nonmetal plus the IDE. So what if you see MgNO3, 2? What would this be? Not nitride, because nitride would just be an N, but since it's NO3, it's a nitrate. So this is magnesium nitrate. Okay, so you just use the name of the polyatomic. You don't change the name of the polyatomic, you just use it. So you can have things like sodium sulfate. You could have magnesium carbonate. You could have potassium chlorate. So if you had any kind of metal, when you add the polyatomic, you just use the name of the polyatomic, like as a whole. You don't have to change it. But now, if you're given the name and you got to go to the formula, like potassium chlorate, potassium you know is what? Okay, and it's in group 1, so the charge is +1, right? It's in that first column. So the chlorate, you know the charge. So it is ClO3 with a negative charge. So which charge doesn't change? So that way you know the charge. And what do you see about there? Positive and negative, they're the same. So the way that they're written, it would just be KClO3. Right? Because +1, -1, if you swap ones, it won't change them. So then lithium carbonate, where's lithium? Li with the +1. And then carbonate? CO3 with the -2. So here they're not the same, so I've got to swap the charges. So what would the formula be? Right, so the CO3 is sort of just one of them because of the charge on the lithium tells me I only need one of the carbonates. So it'd be Li2CO3. What if I have calcium sulfate? Calcium is Ca with a +2. And then sulfate is so you just use the whole formula. With a -2. Okay, so the sulfate is the SO4 with the -2. Now do you notice with these, do you see they're both the same? Calcium's a +2, the sulfate's a -2, so they are going to be a 1-to-1 ratio. So they would just be CaSO4. The calcium's a +2, the sulfate's a -2, so they balance. So notice that I don't change the formula of SO4. That is the sulfate's formula, and it doesn't change. So what about this last one? This last one's pretty challenging. So ammonium, we said, was what? So it's NH4 with the plus. And then phosphate is PO4 with a -3. So now, when I swap, what do I have to use? So remember that the charge, because remember the NH4 would be like a +1. So if I take the charges and I swap them, what's that going to do? What's that going to do to my NH4? It's going to have to get multiplied by 3, right? But I'm not going to multiply them. I keep it together. This is where this comes into play. Do you remember in balancing equations? Do you remember that there were compounds in the balancing equations worksheets that had parentheses? They were all polyatomic ions. So you had things like the SO4, parentheses 2. You have things like PO4, parentheses 3. So you would have that. The parentheses is just because they were an ionic compound. And so if you have to assign the charges and swap those, you would put parentheses around any polyatomic that is more than one of them. She didn't have to worry about it for these ones up here because there was only one of those polyatomics. But since there's 3 NH4s, I put parentheses in the 3. Do I have to do anything with the PO4? No, because there's just one of them, right? So the +1 tells me how many phosphates, so I would just have that as a PO4. So for a polyatomic, when you do the swapping, if the polyatomic ends up with more than a 1, you want to put parentheses, and then the number of them goes outside of the parentheses. So like, for example, if I have aluminum chloride. What's aluminum? It's Al, and the charge is +3. And then I know the chloride is right, ClO3, sorry. ClO3 with the negative. Okay, so now I got to swap. So the number of aluminum is, that's the charge on the aluminum, but how many aluminums will I have in the formula? Just one, so it'll just be Al, but ClO3 will have 3 of them. So I'm going to have to put parentheses, ClO3, parentheses 3. So because in the swapping, because the aluminum that's a +3, when I go to swap, I have 3 chlorates. So I have to put a parentheses around the polyatomic, and that 3 goes on the outside. So when you're just doing metals and nonmetals, you don't have to use those parentheses because it's just a single atom. But when I'm talking about a polyatomic, if I have more than one sulfate or more than one chlorate, I have to put a parentheses and then the number outside. So that's the last ones on this list. Take a couple of minutes, see if you can work on those. I'll leave this because there's the 7. Most people end up putting these with like an example or 2 of a molecule and naming on their note card, okay? Those are the only 7. There's a lot of them, but these are the common 7. So those are the only ones to worry about. Give you a couple of minutes, see if you can do, there's 8 of them at the very bottom. Sodium nitrate, calcium phosphate, lithium sulfate. See if you can get those. They're here. All right, let's see if we can come up with these ones. So what is sodium nitrate? So first assign the formula, then figure out the the charge, and to figure out the formula. So sodium is Na with a plus, and then nitrate would be NO3 with a negative. So see that it's 1 and 1. So the way that it's written, that's the formula, NaNO3. So if the charge on the polyatomic and the other ion's the same, it's just a 1 and 1. So what about calcium phosphate? Calcium is and +2. And then phosphate is PO4 with a -3. Now this one, they're not the same, so I'm going to do the swapping. So how many calcium? So I'll have Ca3, and then I know that I have more than one phosphate, so you got to use the parentheses. That's what I put over here. If your polyatomic ion exists with more than one of them in the formula, you've got to use parentheses. So I know that I've got to put, and you put the whole polyatomic in parentheses. I don't have to put the calcium in parentheses. I'm going to put just the polyatomic. And what number goes outside? A 2, right? So the charge on the calcium tells you how many phosphates. So that +2 tells me that there's 2 phosphates. The calcium is a 3 because the phosphate's a -3 charge. So lithium sulfate, lithium is Li with the plus, and sulfate is with the -2 or 2 minus, it doesn't matter. Notice that they're not the same, so I know I have to swap the charges. So the formula for this, Li2, SO4. Now because SO4 is only 1 because of the +1 of the lithium, I don't need parentheses. So do you see the +1 of the lithium tells me how many sulfates, so I don't have to put parentheses since there's only one sulfate. So magnesium chlorate. Magnesium is with a +2, and the chlorate is ClO4 with a negative. So they're not the same, so I got to swap them. So how many magnesium? Go back. So the chlorate. So look at ClO3 is a -1. So it's ClO3, 3 oxygens with a -1 charge. So, like see here. So this means 1 chlorine and 3 oxygens, and the whole thing has a -1 charge. That make sense? Okay. Okay, so now when I swap this, what do you end up with? How many magnesium? Just 1, right? Because the -1 of the chlorate tells me 1 magnesium, and then how many chlorates? 2. So if I see that there's more, then I'm going to have to put ClO4 in parentheses, and the number goes outside. Go ahead.
Chlorate is not 3, it's 4.
Right, chlorate, no, chlorate's not a 4. Chlorate is a -1. The chlorate is 1 chlorine and 4 oxygens. Okay, so remember the 4 tells you how many oxygens. It doesn't tell you the charge.
You have it in the slideshow as ClO3. It's like 3 oxygens.
Oh, that's what you're talking about. So this should be ClO3, and this one should be ClO3. That's what, so you're right. But still, that oxygen would have a 3, that one wouldn't change. But then I do have to put parentheses around ClO3 and then the 2 on the outside. Now, I think it's easier if you have the formula because, again, you're going to use the whole name of the metal and then the name of the polyatomic, okay? So you don't have to worry about, like, changing the end. So K2SO4 would be what? Potassium. And then sulfate. So you don't change it to sulfide, it just stays sulfate. So that SO4 is a sulfate. Now, if you see NH4, this is probably why I added it there. So that is the only positively charged polyatomic. So it's always out front because it's a positive ion, so it's kind of like a metal is positively charged, but you just use the name of it. So this one would be what? That's right. And so in this one, see how I have the nonmetal there, and I do use the first part of the nonmetal plus IDE because it's just a single nonmetal. So BeOH2. Yep. Beryllium, and you just use the name of the polyatomic. And then the last one. It's aluminum carbonate. So just the whole name of the metal, just like you would otherwise. Then you just use the name of the polyatomic. So it's just those 7. So those 7 are probably ones to make a list. We'll do a little more practicing about them, but the transition metals and the polyatomic ions are really the only kind of weird ionic. Otherwise, they just always follow those steps. They always follow like the same steps each time. So I would say like this is a good slide, slide number 20. That's a good slide to use to look at. Just because one, it'll actually give you each of the metals, what their positive number, their positive charge based on the group, and then you can also review the non-metals. That can help. Plus this shows you those transition. And then going from these, there's the slide that I like in terms of the polyatomics, because that's just a list of those 7. So you don't have to worry about all the other ones that are on those charts. Just these 7, and then just remember ammonium's the oddball because it's a positive charge, so it will be found out front. So when you have metals and you have nonmetals, and they want to do this transferring because metals have very few valence electrons, nonmetals have a lot, so it's really easy to take and transfer the metals directly to the nonmetals. But what happens when you have 2 nonmetals that have either the same or very similar numbers of valence electrons? If that's the case, then they can't transfer. They're going to end up having to share. So one example is how hydrogen forms a diatomic element, H2. So hydrogen, if you look on the periodic table, you see that hydrogen has 1 valence electron. Remember, if it has 2, it'll make it like helium, because helium is number 2 and it's a noble gas. Remember that first energy level only holds 2. So the purple hydrogen cannot pull the red hydrogen's electron away, or vice versa, because they have the same pull. They both want each other's electrons. The only way they can form a stable molecule is instead of transferring and forming ions, they're going to share. Sharing valence electrons is what creates what they call covalent bonds. Covalent bonds are very stable bonds that help to form and link atoms together. So what ends up happening is this hydrogen, the red hydrogen, gets close enough to the purple hydrogen so that their electrons are basically held between. So that means that these electrons, they go back and forth. The electrons now, they kind of have like 2 atoms to span back between. So they go from the purple hydrogen to the red one to the purple to the red. So this means now the purple hydrogen can act like it has 2. It acts like it's like a noble gas. Same thing with the red hydrogen. So the red hydrogen now can act like it has 2, and that creates this stability. So because those 2 electrons are now being shared, they call this a single covalent bond. They can use the Lewis structure, where they use just a line, to indicate that pair of electrons. So I'm sure you've seen molecules just with like a line between 2 atoms. That means that it's a single pair of electrons that's being shared. So hydrogen does this, chlorine fluorine, bromine, iodine. They all exist in nature as Cl2, F2, Br2, and I2. So you don't just see a bromine atom. You'll see bromine existing as what they call diatomic, which means two. They call them diatomic elements. And all of these, chlorine, 1, 2, 3, 4, 5, 6, 7, right? So chlorine has 7 valence electrons. If you look, it's at the top of group 7. So this chlorine and this chlorine share a pair of electrons between them. And do you see that now each one of them has 8? So that creates this stability. Chlorine does this, bromine does this, iodine does this, fluorine. They only form a single bond, single covalent bond, because they have 7. If they share 1 electron with another atom, that's going to create stability. So you will see the chlorine with this dash to another chlorine. Now these electrons, the electrons that are around the chlorine, but they're not part of the bond, they call these non-bonding. These are non-bonding electron pairs. These electrons, they belong to the chlorine. They're not shared. So hence the name non-bonding, because they don't form bonds. But do you see that they give chlorine their 8? So chlorine's got 1 line, which is 2 electrons, plus 6 around its outside. So now it has its total 8. And same thing with the other one. So you would see the same thing with fluorine and bromine and iodine, is that the fluorine would form a single covalent bond with another fluorine, 7 and 7, but that shared pair in between is what creates the bond. But these fluorines have non-bonding electrons. They're only sharing 1 pair. So out of nonmetals and hydrogens are the only ones that do this. Metals do not form covalent bonds. Only nonmetals and hydrogen. So we've actually already just named 5 of the nonmetals, and they only ever form single bonds. So fluorine will only ever have a single bond. Chlorine, bromine, iodine, and hydrogen. They will only form a single pair, a single covalent bond. So if you look at the periodic table, that only leaves what? Right, so we took care of hydrogen, and we took care of all of group 7. So it really only then, the nonmetals that are left are the ones that are in groups 4, 5, and 6. So that means now we just about carbon, nitrogen, phosphorus, oxygen, and sulfur.
Okay, so on this, on the printout that I did, it already has nitrogen and oxygen. So are those like not in that?
They're in there too. Yeah, so those are the other ones. So here shows like how chlorine shows 2 chlorine atoms forming a single covalent bond. Right, so you can see the dash. Sometimes they call the electrons that don't form any, that belong to the chlorine, the lone electrons or non-bonding electrons. Those are the 2 terms you might see referring to the electrons that are not part of a covalent bond that belong to a specific atom. But now we're looking at these. And in fact, these are the ones that we really end up spending time on. So, and there's just these 5. There's carbon, nitrogen, oxygen, phosphorus, and sulfur. So do you see that carbon's in group 4? Carbon's in group 4A. Nitrogen and phosphorus are in group 5A. Oxygen and sulfur are in the group 6A. So it's really just these 5. So carbon has 4 valence electrons. So in order to be stable, it has to have how many? 4 more, right? It's going to end up having to have 8. So carbon, it has 4 valence electrons. So the only way that carbon can be stable is to have 8. So it is going to have 4 bonds. It's going to have to form 4 covalent bonds, and that will give it the octet. So 4 valence electrons form 4 shared pairs with other atoms in order to create that stability. What about nitrogen? Yeah, nitrogen. Right. So nitrogen has 5, right? 5 valence electrons. It's in group 5A. So I know that it is going to need 3 covalent bonds because it's going to need the octet. So you're going to end up having to form pairs. Any electrons that are not paired are going to have to form covalent bonds to become stable. Well, carbon doesn't just have to form 4 single shared pairs of electrons. Carbon can actually form more than 1 bond with other atoms. The goal, though, is just to make sure it has a total of 4. So do you see in this one how carbon has 4 single bonds? So those would be 4 individual bonds. But then, in fact, carbon can form what's called a double bond. A double bond is where you have 2 pairs of electrons or a total of 4 electrons shared between carbon and another atom in order to create stability. In fact, it's even possible, not that common, but it is possible for carbon to even form a triple bond, because that would be 3 pairs of electrons, and then 1 more pair of electrons would give it its total of 8. So do you notice around carbon, you'll always have 4 lines? Okay, there's always 4 lines, and there's never non-bonding electrons. Carbon always uses its electrons to form bonded pairs. Nitrogen, looking at nitrogen, and in fact this would be phosphorus as well, because phosphorus can do this, but nitrogen, notice that nitrogen can form 3 covalent bonds. So N can have 3 lines attached. In any combination, you could have 3 single bonds, like the top one. You could have a double bond and a single bond, or you could even just have a single triple bond. So when you look at this, do you see that in all of these combinations, nitrogen has 1 pair of electrons that are non-bonding that belong to the nitrogen, and it's going to share 3 pairs of electrons in some combination. Phosphorus can do the same thing. So phosphorus could end up with 3 singles, or phosphorus could end up with a double and a single, or phosphorus could even end up with a triple. Oxygen's the only, and sulfur are the other group, group 6. So you know that means that they've got 6 electrons. That means they've got to form 2 bonds. So notice oxygen can form 2 single bonds, or oxygen can form a double bond, but that's the max. Oxygen can't form a triple bond because it only has the ability to share 2 pairs of electrons in order to become stable and have its 8. So carbon's got to have some combination of 4. Nitrogen's going to have some combination of 3. Oxygen's going to have some combination of 2, either 2 singles or 1 double. But that's the maximum. Same thing with sulfur. So sulfur can have a double or 2 singles because it's in group 6. So here's their example. The example for this one is CH4. And so in this is a little bit different than ionic in that I'm not going to give you like random numbers of them. You will always get a formula. In fact, the formula that I'm giving you, these examples are really the most common ones. They're pretty simple. We're not going to make them any more complicated than this. But in this, I have CH4. So the formula tells you exactly the number of atoms in the molecule. So you don't have to figure it out. Covalent molecules, the formula tells you the exact number of atoms. I don't have to do any charge swapping or anything like that. The formula tells me how many. So CH4 tells me that I have 1 carbon and I have 4 hydrogens. So the rules, what I do is I list the atoms. I list how many electrons and how many bonds each of them needs. So for carbon with 4 hydrogens, I have 1 carbon and I have 4 hydrogens. So that's the formula. Carbon, I know, has 4 electrons and needs 4 bonds to make 8. Hydrogen has 1 electron, and hydrogen only needs 1 more electron to have 2, because remember, that makes it like helium. So just remember, hydrogen's kind of the oddball that way. Hydrogen never forms more than a single bond. So then the second step, I'm always start with the atom that needs the most bonds. So when I look at carbon versus hydrogen, carbon needs 4 bonds, so I'm always going to start with that first. So whichever atom needs the most bonds, you always put it down, and I say like make it the center. So the atom that needs the most bonds is always going to end up in the middle. And you're going to put things around it to try and create the stable octet. So I'd put the carbon with 1, 2, 3, 4. Then I'm going, can you see that I need 4 pairs? I need to share 4 electrons, and I have 4 hydrogens. So by putting 1 hydrogen at each of the electrons, pairing them with the carbon, then that's going to put a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. So remember, like with those valence electrons, you never end up with more than 2 up, 2 down, 2 left, 2 right. Those form those single covalent bonds. And then I could take this and swap it into the line structure or the Lewis structure, where it's just a carbon in the middle with 4 single bonds, a hydrogen attached to each. You can see that hydrogens all have 2 in this. And then the carbon has 8.
So in this case, there's no non-bonding in that.
Carbon doesn't have non-bonding electrons. Carbon has 4 electrons, and every single electron forms some kind of covalent bond. Same thing with hydrogen. There's no non-bonding electrons, because hydrogen, when it has 2 electrons, that makes it like helium. So that's all it needs. So you won't have now nitrogen, oxygen, sulfur, and phosphorus, they have non-bonding electrons. And then the halogens, the chlorine, fluorine, bromine, and iodine, they have those non-bonding electrons are the electrons that belong to an atom and don't form a link to another one. All right? So, steps. So we did this one, right? So we ended up with this. Carbon with 4 single bonds to the hydrogen. So what about NH3? So NH3, how many, when you look at nitrogen and 3 hydrogens, nitrogen has how many electrons? Total, but how many electrons in its valence shell? Because remember, that's really what you want to know. That's the group. So the number of electrons in the outer shell is always its group number. So nitrogen has 5 electrons. Hydrogen's in group 1, so I know hydrogen has 1 each. Hydrogen never needs more than 1 bond. But nitrogen needs have a total of 8, so how many bonds will it need to form? 3. So do you see that with 5 valence electrons, I need 3 bonds to equal 8? So the number of valence electrons, which is the group number, plus the number of bonds has to equal 8. So I list them. Now I'm going to start with the atom that needs the most bonds. So in this one, which one needs the most, nitrogens or hydrogens? So I'm going to put the nitrogen down first, N, dot, 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 right? So there's the 5 electrons. And remember to spread these out. You may have to move them around, but spread them out. Now, I've got to add 3 hydrogens. So where will I add the hydrogens? Yep. So I'm going to add a hydrogen here and form a single bond. Add a hydrogen here, form a single bond. Add a hydrogen down at the bottom, and a single bond. And you see in doing this, now you can see that nitrogen has 8 around it, 2 up, 2 down, 2 left, 2 right, and each hydrogen has 2. I've used all the atoms. NH3 is a nitrogen with 3 hydrogens covalently bound or single bonded to it. And if I was going to do the Lewis structure, I would just have a little dash to each H. So H2O, formula, hydrogen, hydrogen, oxygen from the formula. I told you, you will use the exact formula. You don't have to figure out the formula. You'd always have the exact formula. So I know that hydrogens are 1 electron, and how many bonds? 1, right? Because they just want 1. They only need 1 bond to be like helium. So I will tell you, hydrogens are never the center. They're always around the outside because there's only a single bond to them. So they always kind of get added at the end. But oxygen has how many? 6. That means it needs how many to make 8? 2 bonds. So that tells me which one to start with. I start with oxygen with 1, 2, 3, 4, 5, 6. And remember, it doesn't matter where your dots are. You should just make sure you spread them out. So you should have 2 dots on 2 sides, single dots on 2 sides. I don't care where they are. So it would be completely fine if you decided that you wanted to have it like that. That's fine, okay? The key thing is that you are only going to end up with 2 pairs on one side of the oxygen and 2 singles on 2 sides of the oxygen. So now I can see that I've got to add my hydrogen, so where do they go? Yep, wherever the singles are is where you're going to form the covalent bond. Covalent bond, H. So wherever your single electrons are around the oxygen is where you add the hydrogen and form a pair. So I've got like 1 purple dot and 1 blue dot. So that represents that covalent bond. And if I switch this to the Lewis structure, I have that. Would it be fine if I had this? Yeah, okay. And if you remember in lab last week, like you could build this and kind of flip it around and make it look different, but as long as you have an oxygen with 2 pairs of non-bonding electrons and then 2 lines, 1 to each hydrogen, then it's right. They might be up above and below or left and right, or they might make like an L. All of those would be fine. Same thing with this ammonia, NH3. If I had my 2 dots here, this is correct, okay? So you could have your 2 dots on any side. The other 3 sides have a single dash to a hydrogen. So those would be fine too. So don't get like hung up that like, oh, it doesn't look exactly the way it, you know, I've drawn it. As long as you could like take this molecule, like flip it around, like think like, okay, if I just rotated it a little, it would look just like hers. That would be fine. So now we know oxygen exists as O2. If you give a patient oxygen gas, you give them O2. You don't just give them O. Well, oxygen has 6 valence electrons, and how many bonds does oxygen need to be stable? 2, because remember that means 6 electrons plus 2 bonds is going to make their 8. So if it's only O2, I know I only have 2 oxygens to use. So if I start off with 1, 2, 3, 4, 5, 6, and like I said, doesn't matter how you like write them out, but 2 sides of the oxygen should have 2 electrons, 2 sides of the oxygen should have a single electron. If I add an oxygen to it, 1, 2, 3, 4, 5, and 6. So see where I've done my pairing? Well, O2, I'm done. Now I've got 6 purple dots, I've got 6 green dots, I've put down all the electrons, I'm done, but when you look at it, can you see that they're not stable? They don't both have 8 around them. The purple oxygen has 7, the green oxygen has 7. So this is like at the last resort, this tells you that you've got to make a multiple bond. So you're going to have to make a double bond in order to be able to create this stability. So see these electrons that don't have a pair. These are going to move between the 2 oxygens. So this one is going to move here, and the purple one is going to move here. So you see there's still the purple dots are still around the purple oxygen. The green oxygen dots are still around the green oxygen. So I didn't like just move them over. I didn't take the green ones and put them over on the purple side. They're like in between, or they belong to the green oxygen themselves. But this now creates, you see 8, 6 and 2, and then if I do the same thing, do you see 8, 6 and 2? So that is a double bond. That is a double covalent bond. 2 pairs of electrons are being shared. So you would write this out with 2 dashes. Each oxygen would also have how many non-bonding electrons? 4. Do they have to be at the top and on the outside? No, but they can't be in the space between them. They've got to be around like the outside. So you can put 2 above and 2 on the outside, or you can put 2 on the outside and 2 on the bottom. I don't care. But they can't be in between, because if they're in between, they're sharing. And those purple dots that I've got in that Lewis structure represent electrons that belong to the atom, each oxygen atom, and they're not shared. The lines are the ones that are shared. But you always do double bonds, triple bonds last. Don't try to do them first, because you may not need it, okay? First thing to do is always get all your atoms down. Then, if you need to, you can form multiple bonds. So like, for example, carbon dioxide. So carbon dioxide, carbon has 4 electrons, which means 4 bonds, right? So it's in group 4. Oxygen, we said, has 6 electrons. That means 2 bonds, right? Because we were trying to make 8. So 6 electrons, 2 bonds. So when I start this, which do I put down first? Put down carbon first. Not just because carbon is the first in the formula, but because carbon needs the most bonds. So now I've got to add an oxygen. And it really doesn't matter which one, because they're the same. So I could pick any of these dots to put in oxygen. So I could put it up here. Okay? So I put a red oxygen with 6 dots. 1 dot forms a single bond. Okay? So now I've used 1 oxygen. Now I got to add the other one. So I'll do green. And it doesn't matter where I add it. I could add it here. 1, 2, 3, 4, 5, 6. So someone said, well, why didn't you add the green oxygen to the red oxygen? Right? How do you know that you need to add that green oxygen to the purple carbon? So my answer to that is, anytime I add an atom, I always add to the atom in the molecule that still needs the most bonds. So if you look, before I put this down, how many bonds does the carbon need? Like, how many dots don't have pairs? 3. Can you see that? There's 3 dots without pairs. But oxygen, the red oxygen, how many pairs does it have that don't have a match? Just a single electron. That's only got 1 single. So because of that, that's how I know I've got to put the oxygen on the carbon. Because the carbon needs the most bonds. See if I go back to my color. There. 1, 2, 3, 4, 5. Okay? But now I've done all of it. So now if I put all my electrons, all my atoms are down, now I know I have to form double bonds. So the red oxygen, if I want to form a double bond, the red oxygen is going to form a double bond with what? With the carbon. And I'm going to take and move that red electron and one of the purple electrons between the oxygen and the carbon, the red oxygen and the carbon. So I'm going to move this one. So this one is going to go here. And then I'm going to change and put the purple. Oh, I just erased all that. And put it here. There's not much space between. See if I can make, so now I got 2. My O's still here. 1, 2, 3, 4, 5, 6. Okay? So I made a double bond. So notice that all the red dots are between, either on oxygen or between the red oxygen and the carbon. So I didn't take like red oxygen electrons and put them over on the green oxygen. I kept them. So they're always still going to be like connected to their atom they belong to. So, but then, do you see that carbon and oxygen, the green oxygen and the purple carbon, see this one right here and this one right here? See how those are not paired? So those are still like floating about. Well, they're going to pair off, and they'll do that by moving between the green oxygen and the purple carbon. So I'll end up with a dot here. That moves this one. And then I'm going to move this purple one between. So when you get done, you should still have, the green oxygen should still have all of its electrons like connected to it. The red oxygen should still have all of its red electrons connected, and same thing with the carbon, but they're sharing pairs to create the stability. So if I was going to take and do the Lewis structures to this, I would have this. 2 dashes between the carbon and the oxygen on either side. It would be fine if you wrote it out like this. It would be fine if you wrote it out like this, straight across. We'll talk about geometry in the next class, like why. Okay, so between now and next time, there is N2, so you can do the structure, try to do the structure for N2. There is CH2O and then HCN. So see if you can do those 3. We'll do those ones, and then we're going to talk about like what is shape, why is shape important, talk about polarity, and then the naming. So naming of covalent bonds is a little different than the naming that you've got for the ionic ones. Okay? So we'll talk about naming next time too.